Okay, so what I've done here is I've just set up a bit of a model so that we can explain overall stability using a real object, basically. And so we're looking at overall stability. What we're imagining here is maybe this here. Let me just see. Oh, no, I'm sharing screens, so should be okay. So this here might be some kind of concrete foundation, a heavy foundation. This here's a little cantilever platform, so it might be for something like bungee jumping or something like that. I think that's the example I've got. So that's called a cantilever. It just means it's a beam that's fixed at the one end only, and you call that a cantilever. And so that's a cantilever beam. What I've done is I've drawn on the centers of gravity, and so from the stuff we've just learned, we know where they are. So this is a rectangle, provided that's got constant thickness. Well, the centroid of the rectangle is just the position of the center of gravity of the whole object. We're not worrying about out of plane here, into the camera. We're just drawing it on the side. Just doing a two-dimensional problem. And similarly for the little cantilever, if that's got constant thickness and constant density along its length, then the center of gravity will just be in the center of that. And so when we're talking about overall stability, what we're talking about basically is tipping over, so overall stability. So in this case, if we were to load up this cantilever, so you've got someone on the cantilever or some kind of load on the cantilever here, which I have got, let me just find it. So we've got some kind of load on the cantilever, and I've also drawn the center of gravity on that. If you've got some kind of load on that, once that load gets far enough along the cantilever, this is going to topple over, which would be a disaster if it was something real, and you've lost overall stability. While it doesn't tip over, then we would say that that's stable. It's got static equilibrium. It's stable. I'm going to keep rubbing out the center of gravity. So let's have a think about what we've got here. So the whole point in center of gravity is we can say if we represent the force that is the weight of this box by just a line force, then we know that that force is going to act through the center of gravity. So you're going to have some kind of force downwards here. And we're going to have another, probably smaller force here. And then we're going to figure out a point of rotation. So our point of rotation is here. Often it'll be given a letter A or O or something like that. And so we've got a point of rotation here. Not a very good color, really. We just change to red for the next ones. So again, we've got gravity here. That's the weight of this box represented by a single load, and it will always go through the center of gravity. That's the whole point in the center of gravity. It's where the resultant force will go through. We've got the same for the little cantilever, and then we've got some point of rotation A. And how do I know why have I chosen that A? Just look at it and figure out where it's going to rotate around. So if you assume this surface is strong enough to hold it, then A is just the point that it'll rotate around if it's going to fall over. So that's what we've got. Now, if we add a load to that, so it will also have a center of gravity. How far along can I get this before it falls over? Not very far. Made my weight a bit too heavy. And so it's also going to have a center of gravity, and it'll also have a component of force acting through there. So to figure out whether something's going to be stable or not, what you do is you figure out, and I will change color here, you figure out what the moments are for each of those forces about that point A. So we're looking for lever arms. Lever arm is the perpendicular distance to the force. Okay, so we've covered all that a few weeks ago. So we're trying to find the perpendicular distance to the force, or the line of action of the force. Sorry, my drawings will be rubbish. I have to do this with the mouse, unfortunately. And so we're going to have some sort of perpendicular distance. So this might be F1, say. So F1. This might be D1, so the lever arm 1. And so what we're going to find is that this is called a restoring moment. So the moment from that, it wants to go this way. If it was going to topple over, it would go the other way. Okay, it would rotate the other way. Let me try and line those up again. And so, therefore, this is a restoring moment because it's tending to make this object sit down for the point of rotation. So it's tending to keep it stable. So that's called a restoring moment. These two forces here, if we consider the line of action of this force here, would be straight down here. So your lever arm at the moment, where it's sitting at the moment, is somewhere here. Okay, if we thought about the line of action of that force, What colour do I want to do that in? Doesn't really matter, you know what I mean. And so I'm just doing the line of action of that. So you've got, suppose that was F2, then you'd have D2. Okay, so that would be your D2 there. The lever arm to that force. And so it's also going to have a moment, but this time the moment would be in the other direction. So let me just get, oh, that's annoying. Okay, I'll do one at a time, probably makes sense. So just take this one, running very short of time these days, so I don't have a lot of time to redo things. But we've got some force, it's got a line of action like so. We've got a point A that we're using for our point of rotation, and we're just looking at a point, the point that it will rotate around. Essentially, if it's going to fall over, it will rotate around this point. And then we know that we've got a lever arm D to that. And this time, it's going to try and rotate it this way because of the force in the lever arm. The moment is going to be in this direction. And so therefore, that is an overturning moment. So it's tending to make this thing fall over. Similarly, let me just move that out the way there. Similarly, let me just get rid of everything. For this point here, it's also got a force, probably quite a small force. It's also got a lever arm. Perpendicular distance to the force is the lever arm when you're figuring out your moments. So the moment of a force, so this might be D3 or something like that. And so that is also an overturning moment. So relative to this point A in the corner here, it wants to rotate it that way. So that is also an overturning moment. So it's wanting to rotate it this way. The reason it's stable at the moment is because it's, okay, well, that's what we're talking about. So let me get rid of that. So what we're saying here is, what will happen is, what I'm doing by moving this little block along, I'm increasing the lever arm between this point and the perpendicular distance to the force that is the weight of that block, which will always go through the centroid. So if I keep moving that long, I'm increasing the lever arm, so I'm increasing the moment. And eventually we'll get to a point where this thing will fall over. So now we know that the overturning moment, so if we add up the moment from the force due to the weight of the cantilever, we add that with the moment due to the force from the weight of this object, it's now greater than the restoring moment. And the restoring moment being the force due to the weight of this foundation times the lever arm to the rotation point. So the overturning moments now exceed the restoring moment, so we've lost stability and it'll fall over. So it does not have overall stability. So that's essentially what we're looking at. And when you're doing a practical problem, what will end up happening is this might not be a simple shape, it might be a compound shape. So you might have to figure out where the center of gravity of that is and what its overall weight is. Similarly, for your foundation, you might have to calculate where the center of gravity is and then the total weight, and then figure out those. And then you'd figure out calculate the restoring moment, calculate the overturning moment, and then figure out whether it's stable or not. So if you did the calculations in this, you'd find it was stable, but if it was over here, you'd find out that it wasn't stable. That's the basics of what we're talking about, so now we'll go on and do an example.